Welcome everyone to lecture 10. Okay, today's lecture we're going to discuss total energy. We're going to review that, and then we'll introduce the concept of linear and angular momentum, mostly about linear momentum, and I'll mention angular momentum. Okay, the last time we spoke about kinetic energy, 1/2 mv squared. Don't forget that half, and don't forget that factor of 2 in the square, right? If you double the speed, the kinetic energy increases by 4 times. If you increase your speed by 10 times, then 10 squared is 100. Your kinetic energy increases 100-fold. Okay, potential energy, gravitational potential energy was the weight times the height, and then we put these together and we defined the total energy as kinetic plus potential. We also introduced the idea of conservation of energy. A conservation law, if you recall, is what you start with is equal to what you finish with. Okay? Yeah, that's better. So here, we're going to talk about conservation of mechanical energy or total energy. The total energy we start with is going to be equal to the total energy we finish with. So let's look at what I call the diver problem. Okay? If you remember the last time I spoke about the diver on top of a cliff, there she is, and she's scared. Oh no! And there's her hair, and she's standing there, and then she's going to jump, because the tourists want her to jump, only 2 legs, and there she goes. Ah, okay. So here's the problem. Consider a 40-kilogram diver standing on top of a cliff with a total energy of 80,000 joules. First question is, how high is the cliff? How high is it? Well, the only equation we're using is this conservation law. Now, at the top, she's standing. What does standing mean? Standing means she's not moving. So I'm going to write this specifically. Standing. This means that V equals 0. And that means that the kinetic energy at the top is equal to 0. Therefore, her total energy at the top is equal to her potential energy, mgh. Okay. We know the total energy. Total energy doesn't change, 80,000 joules. And that's equal to mgh. Now, as in all the mathematical equations we deal with, we know everything in the equation except for the one thing we're trying to find. What are we looking for? Height. What is the height? H. Do we know the mass? Yes. 40 kilograms. Do we know g? What is g? G is not gravity. Be careful. G is the acceleration due to gravity. And yes, for us, we're taking g to be 10 meters per second squared. So let's solve for h, okay? Solve for h. What does that mean? We need h all by itself. If I divide both sides by mg, the mg's go out and I'm left with just an h. So I'm going to rewrite this as H equals 80,000 joules. Oh, what's a joule? Oh, yeah. It's a kilogram, meters squared per second squared, divided by, now we have M. What was M? It was 40 kilograms. What is G? G is the acceleration due to gravity. You better know this by now. 10 meters per second squared. Now, this answer has to be a height, so the total answer must have units of just meters. Height is in meters. That means all the other units had better cancel if we did our algebra correctly. So let's say a prayer and hope our units work out. All right, we have kilograms divided by kilograms. Out. We have seconds squared divided by seconds squared. Out! We have meters squared divided by meters. One of the meters squared goes out, and that goes out. So we're just left with meters. Wow, isn't that great? So our answer is 80,000 meters divided by, what's 40 times 10? I believe it's 400. How do we do this? You can use a calculator, or you could just like think. I know it's scary, but let's try. Get rid of 2 zeros. 4 into 800, I believe, would be 200. 200 meters. So what is the height of the cliff? 200 meters. Fantastic. Now, we still have the hard part. The second part. How fast is she moving when she's halfway down? Halfway down. Well, we could do a lot of fancy stuff, and we could do long stuff, and we could do confusing stuff, or, here comes that word again, we could stop and we can think. So let's try to think what's going on. What's her total energy when she's halfway down? Her total energy. Well, by conservation of energy, her total energy is still 80,000 joules. The total energy is not changing. Okay? So what changes? Well, when she's halfway down, does it make sense, is this logical to you, that half of her energy will be kinetic and half will be potential? So if her total energy is 80,000, does it make sense that her kinetic energy is what? Is 40,000 joules, and her potential energy is also 40,000 joules. What does it add up to? It adds up to 80,000. Halfway, half her energy is kinetic, and half her energy is potential. Now, what's the question? What is her speed halfway down? Well, what symbol are we looking for? Speed. Well, we're looking for V. We're looking for V, right? So halfway down, watch. Kinetic energy, we just said, is 40,000 joules. So what is kinetic energy equal to? Well, the definition is 1/2 mv squared. Now, once again, we have a formula, and once again, we know everything in that formula. Everything except for the one thing we're looking for. What are we looking for? We're looking for V. We know 40,000. We know a half. We know m. Remember, m was 40 joules? Okay, so let's 40 kilograms. Sorry. 40,000. What's a joule? Kilogram, meters squared per second squared equals. Okay, follow with me. 1/2. What was m? M was 40 kilograms times V squared. We okay? Let's look. Half of 40, I can do that. This is 20 kilogram times V squared. Look, kilogram on each side. All right, let's divide both sides by 20 kilograms, shall we? This way, we get V squared all by itself. You see, kilograms go out. And we're left with, I'm going to rewrite the V squared, is equal to 40,000 meters squared per second squared divided by 20. Okay? What's 20 into 40,000? Let's take a 0 away. What's 2 into 4,000? I believe that's equal to 2,000 meters squared per second squared. So V squared is equal to 2,000 meters squared per second squared. I'm just going to continue here. Here's what we have. V squared is 2,000 meters squared per second squared. How do we solve for V? You remember? V squared. What we need to do is take the square root of both sides. So V is equal to the square root of 2,000 meters squared per second squared. All right. Meters squared per second squared, the square root gets rid of the square. So this will be meters per second. Now I have the square root of 2,000. Here we go with square roots. Well, you have a calculator. You could certainly use your calculator, or we could try to use our brain. Let's use our brain for a second. Let's start doing some squares. What is 20 times 20? Well, 20 times 20 is 400. 30 times 30, well, 30 times 30, 900. 40 times 40 is what? 1600. 50 times 50, what is that? 2500. 5 times 5 is 25. So 50 times 50 is 2500. 40 times 40 is 1600. This is 2000. So the answer should be between 40 and 50, right? 2500 or 1600. So look at, this is all I care about. This is approximately equal to not 40, not 50, I don't know, 45 meters per second. Use your calculator, but I don't really care. That answer is close enough for a multiple choice exam. Okay? So we solve for the speed. Okay. One last thing. Again, listen to me. Remember I just said, what is the speed halfway down? Remember her total energy was 80,000. 80,000 joules. So let's see, what's her speed when she's 3/4 of the way down? 3/4 of the way. So she passed the halfway point. Now she's 3/4 of the way down. I'm not going to do it for you. I'm going to let you figure it out. When she's 3/4 of the way down, 3/4 of her energy are going to be kinetic, and only 1/4 will be potential. Well, 1/4 of this, of course, is 20,000. So 3/4 of the energy is her kinetic energy. So her kinetic energy should be 60,000 joules. And that's 3/4 of the way down. So how do we solve the speed? We play the same exact game. Instead of setting it equal to 40,000 joules, the kinetic energy, this is what we have. We have 60,000 joules equals 1/2 mv squared. Now, I'm going to be very sloppy. Okay? 60,000, joules, kilogram, meters squared per second squared is equal to, remember the mass was 40 kilograms? So half of 40 was 20 kilograms v squared. Take out the kilograms on both sides. Divide 20 into 60,000. Does everybody see you get 30? You get 3,000. So v squared is going to be 3,000 meters squared per second squared. So v is going to be the square root of 3,000, and that'll be meters per second. What is the square root of 3,000? Again, 50 times 50 is 2,500. 60 times 60 is 3,600. I don't know. So I'm just going to play and guess about 55 meters per second. All right, so that would be her speed 3/4 of the way down. So as she goes down, she's getting faster and faster and faster. Why is she getting faster and faster and faster? Because of the acceleration due to gravity. Every second, her speed is increasing by 10 meters per second. But again, we don't know anything about the time. All right, let's jump over to momentum. Linear momentum. Momentum is a phrase often used in sports. That team has a lot of momentum, means everything's going their way and they can't lose and they're heading for a touchdown or whatever, okay? Let's look at what we're going to discuss. Linear momentum. Now, what symbol would you like to use for momentum? Well, the obvious answer would be M, momentum, right? However, it gets very confusing for people when you use M for momentum and M for mass, okay? Or M for meters. So linear momentum, we're going to represent by a small p. Small p. This is linear momentum. And it's simply defined as the mass of an object times the speed. Actually, times the velocity, but we'll talk about that in another lecture when we do vectors. All right, so this would be kilograms times meters per second. So P is just MV, and the units are kilogram meters per second. What unit should we call it? Well, I'd love to call it a Mancini, but nobody else in the world would go along with that. So we don't give it a unit name. So this is just kilogram meters per second. And that's the unit of momentum. So let's talk about momentum for a second. Okay? We've already spoken about a conservation of energy. Do you remember what that says? The total energy we start with is equal to the total energy we finish with. I'll call this COE, conservation of energy. The energy you start with, the total energy you start with is equal to the total energy you finish with. Now, we're going to have another law. It's going to be conservation of linear momentum. I don't care. Conservation of linear momentum. COLM. How's that? I'm going to give you a very, very simple little problem that we're going to do. What this says is that the total momentum you start with is equal to the total momentum you finish with. Total linear momentum that you start with is equal to the total linear momentum that you finish with. Okay, so let me give you a simple problem, a very typical quiz or exam problem. Before I do that, let me give you another example of conservation of linear momentum, okay? Imagine, I don't like guns, but imagine I have a gun. Imagine this pen is a rifle, and the top is the bullet. And this is my system, and it's sitting here. So here's my system beforehand. Nothing's moving. If nothing is moving, remember momentum, linear momentum is mv. If nothing is moving, what is the total momentum? 0. So my initial momentum of the system is 0. Now, I fire the gun. What happens? When you fire the gun, the bullet goes this way, but what else happens? What happens is, we call it recoil. The rifle goes backwards. Why? Why does the rifle go backwards? Well, let's see. When we started, nothing was moving. The total momentum of the system is 0. Conservation of linear momentum says what? It says the total momentum never changes. So if we start with 0 momentum, we must finish with 0 momentum. So watch. You shoot the bullet with a momentum going that way. Let's say it's got 50 units. Make it up. Kilogram meters per second. If it's got 50 units plus, the rifle goes this way with 50 units minus, because it's in the negative direction. When you add up plus 50 and minus 50, the total is 0. So you start with 0 momentum, you finish with 0 momentum. Now clearly, the bullet moves very fast, has a very big speed, but the bullet's mass is very small. The rifle has a very big mass, big M. Its recoil velocity is very small, right? You don't want a rifle recoiling at 200 meters per second. It would take your arm off. So, conservation of momentum. The bullet, small mass, big velocity. The recoil of the rifle, big mass, large mass, and very small velocity or speed.